Okay, hi everyone. Today we are going to talk about one-way ANOVA, analysis of variance. And what we will do first is we will briefly introduce the analysis from the perspective of hypothesis testing. Okay, and then we will go ahead and open our data set and we'll analyze the we'll apply this analysis. Okay. All right. Let's take a look at what the test analysis of variance, ANOVA, what do they do? Okay. And here is a good figure that we can that help us understand what they do. Okay. And usually for ANOVA, what we do is we have typically we have more than two groups, or in this example, 3 treatments. And what we are trying to do is we are trying to see if there's mean difference for these different treatments, or a mean difference for these different groups. What's mean difference? That is the difference of these different means. Okay, so for each treatment, we have mean, we have another mean, we have the third mean. Okay, so whenever you are trying to see if there's different groups, if they, if you want to examine if they are different, then you can use this mean difference examination to see if they are different statistically. Okay. One thing that I want to point out here is if you see here it's population 1, 2, 3. So this treatment, you can think of them as it's treatment, and we have a lot of people could potentially receive this treatment, treatment 1. And then in this specific sample, we have these many, 15 of these participants. But this population will be all these potential participants that are like these 15 who participated. So again, here is the idea of population and sample. What we are testing for all of these hypothesis testing, we are testing the population. We are not testing the statistical significance for the sample, because whatever we have in the sample, it's a fact. Okay, so it's not probability. Probability is for the population, for the ones we do not have data with. Okay, so that's about population, sample, and all of these hypotheses, hypothesis, no hypothesis, and alternative, they are in terms of population. And this is important for you to know. And statistical testing is for generalization. Okay. All right. After having this concept, we can just state our null hypothesis and alternative hypothesis. And if you recall again, usually the null hypothesis is the one that do not have effect. And it's the one that there's no difference. Alternative is, on the other hand, it's an opposite to your null hypothesis, or you have read that they are the null hypothesis and the alternative hypothesis, they are mutually exclusive. So in this way, we can logically conclude if we reject one, we can accept another one. Okay, so in this in our example, ANOVA, the null hypothesis is the mean. The treatment means are the same. Okay, so we have 3 treatments, like you have see here, and the means are the same. And again, here you see that in the null hypothesis, it's represented as mu1 equals mu2 equals mu3. And again, there's mu1, mu2, mu3. These are for the population, not the sample. The sample means are the M's here. It's already calculated. They are facts. You don't test them. But we use these data to further make generalization by this statistical testing. Okay, so or another word you can say is the treatment conditions have no effect on the participants' scores. If we say we are testing the scores from these three treatments. Okay, and since alternative hypotheses are hypothesis is mutually exclusive with no hypothesis. In our case, it would be, since the no is have no effect, or the means are all the same. The means from these three treatments are all the same. So the exclusive one for that one would be, for the null hypothesis, would be at least one mean difference is different among the population. That could be all three are different. Could be two of these are the same, but another one is different. It could be any two of these. So all of these are the possible alternative. Okay, so with that in mind, we can go ahead and analyze. By analyzing, we basically calculate the, in this case, is F statistic. Okay, and if you recall, what we do in hypothesis testing is we have the specific distributions, and then we use the distribution as our reference, since they are the model, as our reference to see where our calculated statistic locate. Okay, so for example, these are F distributions, and you see here on the side, it shows you the degrees of freedom. So for any F distribution, if you have the specific degrees of freedom for the numerator, for the denominator, then you have a fixed reference F distribution. Okay, so you can compare your F value calculated from the data with this reference distribution. Okay, so that's about the distribution. And here's an example from our textbook for the degrees of freedom of 2 and the numerator 15 and the denominator, we have this kind of shape here. Okay, and with the specific degrees of freedom, we know the specific distribution. In another word, we know all these F values on the x-axis. Okay, so here's the, on the x-axis, it's all F values. Okay, even though they are not written out, but you know, it's there. And on the y-axis, it's basically the probability density. But what it does is, as long as we have this specific information, we can know the probability, because probability is the area under the curve. Okay, under the curve. So what we do here is you see that here's the 5%, 1%. These are the typical alpha value or the significance level. I'm also including them in the next slide. So what does this 5% mean? Means that all of this area, this whole area shaded here, if we calculate with the integral, then we will find out that this is exactly 0.05, because the whole area under this curve is 1, which is probability of 1, 100%. Then this little part is 5% here. So what we do basically is we are trying to see whatever F value we have from our data and trying to see if its probability is greater or less than the significance level we chose. Okay, and the significance level, again, these are arbitrarily decided by researchers, and usually in our field it's 0.05. Okay, so for example, if we have F value that is between 2 and 3, for example 2.51, then we are able to make a decision if we are going to accept or reject the null hypothesis. Okay, by what? By the probability associated to this F value. If the probability is very small, that means it's very rare under this assumption. Okay, because the probability is very small, we would reject this null hypothesis. Okay, so when the probability is very small, we would reject the null hypothesis. And how small? The cutoff point is our significance level, 0.05 or 0.01. And then typically, in the next slide, I showed there are 2 ways. The textbook showed you the traditional way, the hand calculation. You need to find the F value from the data, and then you compare the F value with the critical value associated to the alpha, the significance level chosen. Okay, we'll just go ahead and move on to the next slide here. So what I'm trying to say is the textbook introduced you this way. You state hypothesis and you locate the critical region. Critical region is basically the F value and associated to the significance level. Here I said the significance level is also cutoff probability that we choose. For example, if we select 0.05, then the critical region will be, for this specific distribution, will be 3.68 and beyond. That means whatever above 3.68 for that F value, it would be very small probability, okay, because any of these probability beyond that, the tail would be even smaller. So it would be smaller than our cutoff point for the probability 0.05. So we would reject the null hypothesis in that case. So by following this traditional hand calculation, we basically find our F, we calculate our F value, and we compare that F with the F of critical value, which is 3.68 here. So basically this critical value here is 3.68. And we compare that with 3.68. We compare these two. This F is calculated. Okay, and remember that's the variance between divided by variance without the treatment effect. Okay, so this is one way we can make a conclusion in terms of the null hypothesis. But you will see that in this statistical software, what we do is we find the statistical software calculate the F value for us. Okay, so it compute and test it. So we got the F value. And what it does is instead of finding the critical value, it provides us the p-value associated to that specific F value just calculated here. So for example, in this case, the F value, just say it's 2.23. Instead of finding the critical value, in this case, we find the corresponding P. Here, P is 0.1241. Okay, so by finding the corresponding P value, we don't really need to find this the critical value. This way, we can just directly make a decision based on the P, the probability associated to the F we just calculated. Okay, how we decided? Let's take a look at this P value here. The P value here, it's 0.1241. All you need to do is just to see if this is greater than the cutoff probability, which is the significance level. Okay, and most cases we use 0.05 just to see if it's greater than 0.05 or less than 0.05. And in our case, this is definitely greater than 0.05. Okay, significance level, we just say if it's a 0.05, this is the probability is greater than, this is greater than 0.05. That means it's not extremely small probability, it's quite large probability. So in this case, we would need to make a decision, which is we fail to reject because it's it's relatively large probability. It's greater than the cutoff point. So we fail to reject the null hypothesis. Okay, and I will show you in the test how we are going to further make conclusion. Okay. Okay, I just opened the data here from my course. What we will do today is we will create a factor with 3 levels. We don't have one ready. So what we will do is we will just use this variable letter. This question reads, let me make it bigger. Doesn't allow me. Anyway, this question reads, how you see yourself if it's if the society is a ladder, like where do you see? You can copy and paste if you usually you can just highlight the cell, and then there's a little drag you can do and to make it longer so that you can see. But since I'm recording, it's difficult to do that. I'm just going to copy the question here. Think about society as a ladder with high rungs representing high status on the scale below, which with 10 representing the highest and 1 representing the lowest. Where do you see yourself? Okay, so society as a ladder, and then you rate yourself from 1 to 10. Okay, let's take a look. Whoops, didn't mean to do that. Now it makes this too big. Hold on. All right, so this ladder variable now has possible 10 from 1 to 10. Let's see what we labeled from the beginning to represent the specific direction. 1 means the lowest, and 6 is the middle, and 9 is high. We may have 10 because it represents 10. Anyway, what we will do is we will recode this 1 to 9 or 10. Okay. Looks like it's 1 to 9. We don't have 10, or we don't see 10 there. So what we will do is we will recode. We will make this 1 to 5, 1, 2, 3, 4, 5 as low, 6 as middle, and above 6 as high. Okay, so that we have 3 groups. Okay, so what we would do, we go data and recode, maybe transform. Yeah, transform. Let's go transform. Recode into different variables. Let's click that. And what we do here is we select the variable, its letter. Okay, and then I'll just name this a little bit differently, and maybe just include that as society letter. We'll just make this as a low, middle, high. Okay. This label is for ourselves so that we know what they are. So I'm just going to label this a low, middle, high so that we know what they are. Okay, so I'm just going to click change. And then click old and new values. So I'm just going to use range 1 through 5 as 1. I can only put numeric value here. So 1 in our case would be just low, right? And then 6, I just examined, we have quite a lot, 6. So I just grouped 6 as the 1 by itself, means it's middle. Whatever below 6, it's low, above 6 is high. So I just label 6 as 2. And I will label 7 through 9, since we just didn't have 10, 9 as 3, which is high, okay? So by recoding this, 1 through 5, it's 1, 6 is 2, 7 through 9 is 3. Basically, 1 is representing low or below the middle letter. 2 is the middle letter. 7 to 9 is the high. Okay. So I am just going to click OK. Okay, here you see that we have a new, and I'm just going to briefly remake this, since I just talked about 1 is low, 2 is middle, and 3 is high, so that I won't forget and it makes sense to me. So I'm just going to not making it any decimal here. Yeah, great. So now we just created 3 levels for this society letter. So what we are going to do is that we can go ahead and analyze. Okay, analyze. And since we are comparing means, we just go compare means. And one with ANOVA is here. And I'm just going to explore our data here. In this window here, for dependent list, it's the variable that you are interested in terms of measure, in terms of comparing the group difference. So what difference you are interested in, right? So in our case, I'm just going to see if you're, just play with it and see if this distance between Africa and Europe, if you all have responded significant different distances in these 3 different groups. And these society letter. Okay, And what we do, click post hoc, and we will, or maybe we can just check the post hoc later. Post hoc is when you have significance, when you have these mean differences, when the mean differences are significant, and that means you reject the null hypothesis, then you will need to see exactly which groups they are different. Okay, so I'm just going to maybe descriptive and homogeneity variance test, and click continue and OK. Okay, so let's see what we have here. Now we have descriptive statistics. This tells us what we have here. And see, we have 19 responses in low, and 25 in middle, and 13 in high. And we have total 57 valid responses. Okay, and these tells you the descriptive for these three different groups. Okay, and this homogeneity of variance, if you recall, what it does is it tests one of these hypotheses of ANOVA, and that in independent t-test, we also had a similar test. We also had it's called Levine's test. Basically, we are testing if the variance is the same, okay? Because that's the assumption. Variances are the same. So we see the variances, it's significant. That means the variances, the homogeneity of variance, it's not assumed. It's violated. Okay. Anyway, for now we just go ahead and read this. We will come back to this homogeneity of variance. And this is the main test result. Okay. What it tells us here is we have between group, and this is sum square for between group, and degrees of freedom for between groups, and mean square for between groups. And here is the F value. And of course, F value is calculated from the ratio of these two mean squares. Okay, as you've read from the textbook and Dr. Hawley's lesson. So what I want to bring out here is the significance. So for our test, which is the F test here, the F value we calculated, or the software calculated for us, is 4.96. Okay. And our degrees freedom for the numerator, which is the between groups, is 2. And for the within group, which is the denominator, is 54. Okay. This is something that we just talked about. You can check from either way. You can check the these critical value for F test in this case, and compare our calculated F with this critical F value and see which is greater, and then make a decision from there. Or we can, like these computer programs, they calculate, or they report the significance, the probability, which is associated to the F value here. So by this probability, we can make a decision in terms of our null hypothesis. And now you see the probability is 0.01. If our significance level, which is the cutoff point, is 0.05, then you see that this 0.01 is less than 0.05. That means it's extremely small probability. That means we are going to reject the null hypothesis. Okay, when we say reject the null hypothesis, we need to know what the null hypothesis is first, right? So we go back and then visit what's the null hypothesis, right? Okay, so now we are rejecting null hypothesis. That means the null hypothesis states that there's no group difference, group mean difference, or all the means are the same. Since we're rejecting it, that means alternatively, the means, at least one means are significantly different from the rest. Okay, so since we have three groups, low, middle, high, and we don't know which group is different from which one, or if they are all different. So what we do next is we check the post hoc. Okay, and that's what we were trying to do at the beginning. I did not check it at the beginning because it's related to the homogeneity of variance. And if you see here, the homogeneity of variance here is violated, okay, because it's very small probability. This assumption of the same variance is violated, okay? And then what we will do is when we go back to the test, we can just check this. Since we see significant difference, we need to know which group, which groups are different. So I'm just going to repeat this, and then I'll just select for the post hoc. I'm just going to select since equal variance is not assumed. We just saw from this homogeneity of variance, it's not assumed. So I'm just going to all of these are different adjustment when the assumption, when the equal variance not assumed, then they make adjustment, and all these different ones are just different method to make adjustment. So I'm just going to use the Games Hall and then continue. And this way it will provide us all of these, including, since this is not the homogeneity of variance is violated, the assumption of equal variance is not assumed. So we would just go ahead and use this. Okay, move ahead. Let's take a look at this post hoc test. Okay, now we see the post hoc test. Okay, it basically compares each pair. Okay, low with middle, low with high, middle with low, middle with high. Okay, so if you see here, this is the mean difference, the first row with without highlight. So like this one, mean difference. Let me use so now this is the mean difference, and this is the standard error for this mean difference, and this is the significance for this is the probability for such mean difference. See what's the probability associated to that mean difference. Okay, and this is the 95 confidence interval for this mean difference. Okay, so what we do here is mainly we first check the probability, which is the sig here, written as sig. Okay, so these are the probability associated to the mean differences reported here. Okay, so what we see here is we need to recall the cutoff point 0.05. And if it's smaller than 0.05, that means we are going to reject this mean difference. This is the post hocs are like the t-test, similar to our t-test, but they are with adjustment. Anyway, so when these are significant, the probability is very, very small. That means this difference is significantly different from 0. Okay, so that means whatever you see here, the difference is significant. Okay, again, this is also probability test, and what you see when you see this probability, you go back to the null hypothesis. Now, null hypothesis in this case would be the mean difference is not significant the means are not significant different, or the mean difference is 0. Okay, so in this case, I'm just going to highlight here. For example, this row. This row tells us the middle, the ones from middle ladder society, they reported higher mean value for this distance than the high society ladder group. Okay, and this is the mean difference is significant in this case. Okay, so by checking this probability here, you can tell which groups are different. And in our case, it's the middle and the high. And you will also see the same here, except the sign changed in the last row. Okay, because it's the first subtract the second. Okay, so middle subtract high, it's this 2,186. And high subtract middle, it will be negative, because it makes sense when you switch the subtrend and the number you are subtracting. Okay, so what we are doing here is we are trying to see what are specifically different the groups. Okay, and after having this, we can go ahead and further make conclusion that we from this ANOVA test we CF value, when we report, we write this as F, maybe another color. We write this as F, and we included the first degrees of freedom as the first number, and then comma, the second degrees of freedom, the denominator degrees of freedom, 54 in this case. And then we write the F value, which is 4.963. So this is a way of writing this result from the table. And then we can put p-value, p equals to 0.011. Okay. And this is, we know that since this p is small, we can conclude that we reject the null hypothesis. And then there is significant difference. At least one group is significant different from another. And further, we checked which groups are specifically different. Then we found out in the post hoc test, middle, the ones in the middle, they have statistically higher guessed distance between Africa and Europe than the ones from high ladder group. Okay, because this p-value here. Okay, so this is about the testing, and some of you that you see in our textbook, we also have this effect size. Calculating effect size, all you need to do is you can manually calculate. This software doesn't provide us, but you can, by using the table, you can calculate the effect size. Okay, sum square of the between, subtract the sum square of between and within. Then you can divide. I meant you can use the this table information to calculate the eta square. Okay, so that's all for this module. And if you have any questions, don't hesitate to let me know. And after watching this tutorial, you may start with the application quiz. Okay.